WaveOptics Part 8. Last time we had seen the Biprism Experiment. We had seen that it consists of an optical bench. We have a Fresnel's biprism which is used to determine the wavelengths of monochromatic source of light. The optical bench is about 1.5 meters length and 15 centimeters broad with calibration. The 4 movable stand carries a slit whose width can be changed. A biprism lens and eyepiece with micrometer screw is mounted on it. The convex lens is later on added. We will see why. The interference pattern consists of alternate bright and dark bands parallel to the slit. We can measure the length of light using lambda is equal to x small d upon capital D. We measure d and small d. Before that, let us see the ray diagram. That's the biprism. We have the screen or the eyepiece. Rays of light come out from the source S, move towards the screen and eyepiece after refracting through the biprism. They come back to form the virtual images S1 and S2, which act as a coherent source of light to give out the interference pattern here. This is the region of interference. This is capital D, the distance between the source and the eyepiece. So measurement of D is done by measuring the distance between the slit and the eyepiece. So we have measured D directly on the optical bench calibration. Now let us see how to measure the fringe with capital X. This is a central bright band. Let us say that the reading here is x0. After getting the interference pattern, the crosswire of the micrometer eyepiece is adjusted on any reference bright or dark band called the zeroth bright band. Now we consider xn. So the reading of the scale of the eyepiece is measured as x0. The micrometer eyepiece is then moved through the n bright bands. The reading of scale of eyepiece is measured as xn. Therefore, we subtract xn minus x0 to get the fringe width. Capital X is equal to xn minus x0 upon n. The measurement of small d. We introduced the convex lens, if you remember, between the source, the biprism and the screen. Rays of light come out through these virtual images S1 and S2 to form a magnified image on the screen. The distance between these 2 points is D1. Now we move the convex lens towards the screen. What we get is a diminished image D2. Now we know the object distance is u, the image distance here is v. This becomes the image distance v here and this is the object distance. This is according to the principle of conjugate foci. d by d1 is u by v, d2 is u by v. So d by d2 is u by v. d square is equal to d1 into d2. So d is equal to root of d1 d2. So knowing capital D, capital X and small d, we can find lambda using the formula lambda is equal to x small d upon capital D. Multicolor screen over a thin film of oil floating on water. This is a very common thing that one might have observed when oil falls on water or petrol is fallen on rainwater. Let us see why. These are the 2 refractive indices N1 and N2. Rays of light is incident on in here. This is the angle theta 1. It gets reflected and refracted. The refracted ray reflects back in the denser medium and it again refracts to the rarer medium. These 2 rays form the rays of light for interference. Now let us see how. This is theta 3, theta 1 and theta 2, A, B, C, D, E and F. This is the thickness D of that particular film. That's the reflected light. The parallel rays AE and CF have a phase difference due to their different path lengths in different media. The phase difference depends on theta I, the angle of incidence, and the wavelength of light. Rays AE and CF interfere, producing maxima and minima of different colors. At different angles of view, one sees different color. The reflection from the denser boundary has an additional phase change of pi radian. Now let us see what is the actual and the optical path. The phase of light is kx minus omega t. Omega is the angular frequency. V is the linear velocity. Wave vector k is equal to omega upon v. In vacuum, you have rays of light. In medium, this is also a sine wave. The refractive index here, since it's vacuum, n is equal to 1. Refractive index is n of the denser medium. If it travels here as n delta x, when in medium the distance travelled is only delta x. Now let us see why and how. So if the wave travels delta x in medium of refractive index n is equal to 1, that means the phase change delta theta is equal to k into delta x. K is omega upon c if medium 1 is a vacuum. C is the velocity of light, of course. Then the phase change delta theta is equal to omega by c into delta x. If the wave travels delta x in medium of refractive index n, then the phase change delta theta dash is equal to k dash into delta x. K dash is equal to omega upon b upon omega upon v, that is omega upon c upon n, v because v is c upon n, where n is the refractive index of the denser medium. Then the phase change delta theta dash is equal to n omega upon c into delta x, that is equal to omega upon c into delta x dash, where delta x dash will be equal to n into delta x. Delta x into n is the optical path. It is defined as the corresponding path in vacuum for the same time. In vacuum, the optical path difference is equal to the actual path since n is equal to 1. We know that time is displacement upon velocity. So we can write d in the medium upon v of the medium is equal to d in the vacuum upon v in the vacuum, where d is the distance and v is the velocity. The optical path d in vacuum is equal to v vacuum upon v medium into d medium. But v vacuum upon v medium is nothing but the refractive index. Therefore, d vacuum is equal to n into d medium. The path difference produced when it travels from one medium to another is nd minus d. That is equal to n minus 1 into d. If t is the thickness of this layer, the rays of light enter inside, then we can say that if t is the thickness of the transparent plate, optical path difference is n minus 1 into t. Now let's see what is diffraction. When rays of light enter through a small slit, then if the slit is big, then the rays pass like this. When lambda is much less than d, that is the slit width. If it is reduced, lambda is almost equal to d, some rays of light will bend. And when it is still smaller, lambda is much greater than d, then the rays of light will bend still further. So here the plane wavefront does not bend, here it bends visibly, plane wavefront bends, slit axis